Hello everyone, my name is Meng Xiang. Today I'm pleased to present our work, Distribution Free Pretraining in Probability Space. The method is called Evolutionary Dynamic Loss, or EDL. Our goal is to learn a classification loss that is general, transferable, and easy to use in standard classifier training. The key idea is simple. A classification loss mainly depends on the relationship between predict probabilities and the ground truth label. So we learn the loss directly in probability space using synthetic prediction label pairs. Let me start with the motivation. In classification, a model outputs class probabilities and the loss function converts them into a training signal. This signal affects optimization, convergence, and generalization. CE is simple and effective, but its loss shape is fixed. In real training, simples can be very different. Some are easy, some are near to decision boundary, and some are confidently wrong. So one fixed loss shape may not be ideal for all cases. This motivates our questions. Can we learn a useful loss to transfer it to downstream classifier training? This slide shows our distribution-free innovation. Traditional meta-loss methods often depend on real data, task-specific trajectories, and expensive training loops. Our idea starts from the loss itself. For a classification loss, the real image has already become a probability vector. The loss only needs the prediction and the correct label. If the correct class probability is high, the loss should be small. If it's low, the loss should be large. Therefore, we construct the synthetic prediction label pairs in probability space and learn a transferable loss pair from them. Now I will introduce the proposed method. EDL has two main parts. First, synthetic separation in probability space. We generate prediction label pairs and define a ranking signal. Second, evolutionary search with chaotic mutation. We search for a stable and useful loss shape. Together, these two parts allow us to learn a loss without real images in the pre-training stage. This is the full EDL pipeline. In stage 1, we generate synthetic pairs, and each pair contains a probability vector P and a label Y. The EDL network takes P and one hot label as inputs, and outputs a scalar loss. The supervision principle is harder predictions should receive large losses. We evaluate candidate loss networks by its rule, select the better one, and generate new candidates by mutation. After evolution, we obtain the loss EDL loss. In stage 2, we use this learned loss to train real classifiers. The classifier architecture doesn't change. EDL is simply used as the training objective. Now let me explain synthetic supervision. EDL uses synthetic predictions label pairs P and Y. Here P is a probability vector and Y is the one hot label. For binary classification, P can be simpled between 0 and 1. For multi-class classification, P is simpled on the probability simplex. We also cover important cases, such as extreme confidence predictions and boundary confusing predictions. Then we compare two synthetic pairs. EDL outputs two losses, and we compute two difficulty scores. We define delta L as the loss difference and delta T as the difficulty difference. The key condition is delta L times delta T should be greater than 0. This means the loss order should match the difficulty order. In simple words, harder predictions should get larger losses. Next is evolutionary search. Learning a loss function is a loss shape search problem. Because synthetic pairs are randomly simpled, this search can be noisy. So we use the population-based evolutionary strategy. First, we initialize candidate loss networks. Second, we evaluate them by ranking accuracy. Third, we keep the best candidates as elites. The mutation generates new candidates. By repeating this process, the population gradually moves toward better loss shapes. What is chaotic evolution? Standard mutation often uses Gaussian noise, but its search pattern can be limited. EDL uses a chaotic coefficient from the logistic map to control the mutation amplitude. When the chaotic value is small, the step is small, which helps careful improvement. When the chaotic value is large, the step is larger, so helps the search leave bad regions. So chaotic mutation balance exploration and refinement define loss shape search. A chaotic sequence is bounded, but it doesn't simply repeat. For our research, this means we can have both small and large mutation steps. This is useful because finding the good loss shape is not always smooth or easy. Now I will present the experimental results. Our experiment answered two questions. First, does chaotic mutation improve EDL pretraining in probability space? Second, can the learned EDL loss transfer to real classifier training? We evaluate EDL on CIFAR 10 with ResNet 8, 20, and 32. This slide shows the early stage at epochs 0 and 30. The loss shapes are still complex and the population contains many different candidates. This means the search is difficult at the beginning. Evolutionary search is useful here because it keeps diversity and preserves promising candidates through top K selection. This slide shows the later stage, at epochs 60 and 80. The loss shape becomes smoother and more stable. This suggests that EDL gradually learns a better loss surface. A smoother loss shape can make downstream classifier training easier and more stable. We compare chaotic mutation with standard Gaussian mutation. The results show that chaotic exploration achieves better pre-training efficiency. It obtains about 29% lower final fitness and faster convergence. It also improves mean fitness and reduces accuracy variation. Finally, we evaluate downstream classification performance. On CIFAR 10, EDLES chaotic achieves the best results among the listed methods. This result shows that the loss learned from synthetic probability space supervision can transfer to real image classification. To conclude, EDL learns a classification loss directly in probability space. It uses synthetic prediction label pairs and a simple ranking rule. Harder predictions should receive larger losses. Then it uses evolutionary search with chaotic mutation to find effective loss shapes. The learned loss can be directly used as a drop-in objective for standard classifiers. Overall, EDL turns loss design into a data-free, ranking-guided evolutionary search problem and produces a reusable loss prior for downstream training. Thank you very much for your attention.